Arturo has come from University of Vergata today. Vergata. And Arturo was originally a physicist, still is kind of a physicist, and he tells me he was working on nuclear fusion and gravity waves, and now he's moved on to something much more interesting. So he's been working in the auditory sphere since 1999, I think. So he's going to talk to us about these amazing things called otoacoustic emissions today. So thank you very much, Arturo.
Thank you for a nice introduction and for having invited me here. Thank you everybody for having come here so late in the afternoon. And I will try to show you something about otoacoustic emissions that should convince you that they are interesting research topic and a good way to study the functionality of the inner ear of the cochlea. We are a small research group at Rome University. These 5 people are all our group, 4 researchers, 1 PhD student, and our scientific goals are to try to explain some aspects of the physiology of hearing by using 2 distinct approaches and by comparing the results, building mathematical models of the cochlea and running experiments on otoacoustic emissions that are a byproduct of the activity of the cochlear amplifier that permit to test the cochlear function in an objective way, even if rather indirect way. But I will tell you how we can make the relation between otoacoustic emission measurements and cochlear mechanics more precise by using effective data analysis techniques based on time frequency analysis. This is the main topic of the talk. Of course, otoacoustic emissions are a complex phenomenon, and we must clarify the details of their generation mechanisms, because there is not just one mechanism for generation of otoacoustic emissions. There are many of them with different characteristics, and we can disentangle the different components of the otoacoustic response, starting from our knowledge of the characteristics of these components in terms of phase, slope, and so on. And mathematical models help us in this task. One important goal of our group is also to build prototypes of advanced otoacoustic emission data acquisition and analysis systems that use our knowledge about cochlear mechanics to optimize, ideally, the output in terms of diagnostic power. And we are also trying to convince people on the audiological side of research to use this system of advanced system of acquisition of acoustic emissions for the early detection of hearing loss, particularly in the occupational health field, workers are exposed to noise, which is a very big problem. The big problem is to detect hearing loss before it becomes very serious for them, and to detect also objectively, because this is necessary from an also medical legal point of view. We do some research on modeling. We build some nonlinear active models of the cochlea that are based, of course, on the physiological data, which are mostly obtained with direct measurements of the basilar membrane vibration that are obtained on small mammals with laser interferometry. And so we start from this experimental evidence, which is relative to small animals whose hearing system is quite similar, but not exactly equal to that of humans. And we also rely on the physiological data on otoacoustic emissions, of course, which is our main research field. But we don't try to build a very detailed model of the physiology of hearing based on anatomical data. We just try to model the function of hearing with a very quite abstract concept, like starting from the measured input-output function, for example, of the outer hair cells and so on, but not going into the details of the very complex mechanical relation between all the anatomic parts of the cochlea, which is an enormously complex task, which would be too complex for us, and it's also not very good in our opinion, because it implies using a very large number of free parameters in a model, so the model starts to be not predictive but just descriptive after some after a long work. You don't get very useful objects. Of course, as the cochlea is a strongly nonlinear system, we have to get a numerical solution in the time domain, and this may be computationally expensive, so we need some efficient iterative methods for these solutions. And we have a mathematician who is an expert in this field, Daniele Bertaccini, who's responsible for the implementation of these numerical methods for the solution of the model. We physicists work on the implementation of the equations describing cochlear mechanics into the model. Of course, we are interested in comparing the results of experiments on otoacoustic emissions that we ourselves make with the prediction of these models. This has a twofold purpose: to improve the model, having put constraints on its parameters, on its few free parameters, and after that, when we understand from the model how we expect to get what signals we expect to get from a normal cochlea and an impaired cochlea, we can improve the design of diagnostic techniques starting from the model results. From the experimental point of view, we have developed some, we call them advanced techniques from data acquisition and analysis of otoacoustic emissions, which are based on the use of chirp stimuli, which allow us to get high frequency resolution spectra of otoacoustic emissions in a reasonably short time, acquisition time, and it's important to have high resolution spectra because we have to use some time frequency filtering techniques that may work only if we can measure the phase of the response with a good accuracy, and so we need a high frequency resolution spectra. We also use these techniques for the online analysis of the acoustic emission response during acquisition, which is important because we can interact with the acquisition system either with automatic procedures or interactively by the operator to optimize acquisition during the measurement. And we have developed this prototype for acquisition of acoustic emissions based on LabVIEW, which is a very funny way of programming and I enjoy doing it. even if I'm not a very good programmer, so my programs get very crowded very easily, and nobody else can understand anything, and I cannot understand anything after a few months as well. But it is, if one does the things properly, it's a good way of programming these kind of things. And we've made a lot of experiments on otoacoustic emissions recently using these acquisition and analysis systems involving the measure of otoacoustic emission of various kinds in humans. You all know about the human ear, of course. We divide the auditory system in three parts: the peripheric auditory system, and the ear canal is essentially a resonant cavity from our point of view. The middle ear is an impedance adapter and pressure amplifier. We focus our attention on the cochlea, which is a high sensitivity acoustical detector and performs frequency separation of the components of the incoming sound, and with a surprisingly good frequency resolution. Surprisingly, because we have a frequent capability of discriminating frequencies with a relative frequency resolution of a few cents, which is quite surprising for a biological system not made of metal and IQ materials. The cochlea is a very interesting system because it's characterized by nonlinear gain, spontaneous generation of otoacoustic emissions, which are very, very monochromatic signals with bandwidth, very small bandwidth, smaller than 1 Hertz, which are characteristic of each individual ear and last for the whole lifetime of an individual with the same frequency and almost the same amplitude, like acoustical fingerprints. And they suggest unambiguously the existence of some active system inside the cochlea which feeds energy into the system during its operation. And also very interesting are the suppression phenomena in which both the gain and the bandwidth of the cochlea at a given frequency are affected by intense stimulation at nearby frequencies within a critical bandwidth. All these phenomena are studied by psychoacoustics, excluding spontaneous otoacoustic emissions, of course. Psychoacoustics is a very good approach to human hearing because it studies the whole auditory pathway from ear canal to the brain, and so it tells us something about the real thing, the hearing perception itself. But this indirect approach involving otoacoustic emissions may be considered as a useful complement to psychoacoustics because it gives detailed information about the cochlea in an objective way. And you should also consider that it's not always possible to test humans with psychoacoustic techniques because they cannot be applied on children or psychically disabled people, or people who don't want to collaborate for some reason or want to cheat the insurance company or so on. And for this reason, much interest has been drawn by otoacoustic emission objective techniques. You know about the properties of the cochlea rely on some particular functions performed in the cochlea. The frequency selectivity comes from the tonotopicity of the basilar membrane, which is a membrane, you know, that resonates at a different frequency at each place along its longitudinal extension. during along this extension of about 35 millimeters, you have a logarithmic map associating the frequency to the position with almost logarithmic spacing. And the frequency resolution is very good at low levels of basilar membrane displacement, and is degraded going to high stimulus and so high BM displacement levels. Also, nonlinear active amplification of signals is given by the electromechanical feedback provided by the outer hair cells, whose electromotility permit to convert an electrical stimulus into mechanical force, additional force to the basilar membrane, which improves both the gain and the frequency resolution of the system, acting as an active filter, which reduces the bandwidth and increases the gain simultaneously. So the two aspects are related to each other. The detectors are actually a different kind of hair cells, called the inner hair cells, that perform the mechanoelectrical transduction of the vibrations of the basilar membrane, converting them into a signal that goes to the auditory neural pathway to the brain. And at this stage, we cannot gain information anymore with otoacoustic emissions. With otoacoustic emissions, we just get information about the motion of the basilar membrane indirectly, because part of this acoustic energy is reflected back through the middle ear, and we can measure it as otoacoustic emissions in the ear canal. Just to remind what we are talking about, we have the middle ear on the left acting as an impedance adapter, because we have a very high impedance system on the right, the cochlea, and the low impedance stage in the ear canal. Without the middle ear, all the acoustic power would be reflected back, and we could not hear. The cochlea is schematized in our models as a very simple system, almost consisting in two cavities filled with liquid and one membrane, which is the basilar membrane. The fluid can go through the helicotrema from the upper chamber to the lower chamber, and the pressure difference between the two chambers, which is driven by the oval window vibrations. Oval window is connected to the stapes. This pressure difference drives transverse vibration of the basilar membrane. On the other hand, the basilar membrane vibrations due to fluid incompressibility drive some gradient of longitudinal velocity in the fluid, and the coupling of these two phenomena produces the traveling waves of pressure and transverse velocity, very much like tension and current in an electrical transmission line. There is an analog between electrical circuits and the mechanical systems, of course, which you already know. And in this analogy, velocity is the analog of current, and the pressure the analog of tension, and you can talk about electrical impedance and mechanical impedance in almost the same ways. Inertia, of course, is a property of inductance, which is trying to stop variation of the current, and mass does the same with variation of velocity through the Newton law. And so there is this analogy that we use very often because a lot of work has already been done in electronics on these systems. The system is nonlinear, and the interesting fact is that the impedance of the transmission line is not constant, but there is a resonance frequency, a different resonance frequency associated to each cochlear place along the longitudinal direction x. The purpose of the round window on the in the bottom part of the left side of the cochlea is to vibrate in phase, out of phase with the oval window to keep the volume constant of the cochlea. Okay, we already probably knew all this, but this is the equation we start with after having coupled the equation of the incompressible fluid to those of the tonotopical resonant elastic membrane, the first and the second one. We get this passive linear model. In the passive case, we don't have additional forces driven by the outer hair cells, and the model is very simple, and we cannot solve it. The model is linear, and we can solve it in the frequency domain, and everything is very easy. It reduces to algebraic equations, and everything goes very easily. Of course, the model is not accurate because I thought that the system is highly nonlinear, but we can still study it in a perturbative way using WKB approximation for the solution of giving forward and backward waves and treating nonlinearity as a small perturbation. Of course, this is not perfectly accurate, but could work at low levels of stimulations where nonlinearity is still a small perturbation superimposed on an underlying linear regime in some models at least. So the linear approximation gives some information, as you may know, about the WKB solutions which give us information about the propagation of traveling waves back and forth along the cochlea, their velocity. We can use this approximate linear model to understand what happens when a traveling wave propagates along the cochlea, its amplitude in terms of vibration velocity, transverse velocity of the basilar membrane increases approaching the resonant region, the wavelength decreases, and the propagation speed strongly decreases approaching the resonant place. You have these waves that is amplitude amplified and slows down approaching the resonant place. At the resonant near the resonant place, you get the maximum amplitude in terms of vibrations of the basilar membrane, and after that you get a resonant absorption at the resonance. You can, in the WKB approximation, the key function is the wave number, the complex wave number of the wave, whose, of course, whose imaginary part becomes large at resonance and causes resonance absorption. Its real part becomes very large close to the resonance and then goes to zero at the resonance, and this behavior is associated with that slowing down because correspondingly the group velocity of the wave decreases sharply near the resonance. For this reason, the amplification in amplitude that is associated to a given cochlear model is also associated to the time needed to go from the base of the cochlea to the resonant place. When we measure otoacoustic emissions, we measure their amplitude, but also their phase, or the time delay when we measure the impulse response in the time domain. And so the measure of the time, of the delay in time, or the group delay in the frequency domain of these waves is an important method to understand the behavior of this wave number along the cochlea, and particularly near the resonance. And this is related both to the time properties of the response and to the amplitude, to the gain of the system. When we have to model nonlinearity, we go into, of course, into some problems. We cannot use the frequency domain representation anymore, and we have to choose a suitable nonlinear function describing the nonlinearity of the outer Hertz cells. We've chosen to use a very simple phenomenological function to express the property of the outer Hertz cells to respond non-linearly in an intermediate range of stimulus level. The basilar membrane is the vibrations of the basilar membrane as a response to stimuli of different level has been measured very accurately on animals, and it turned out that the response is almost linear at very low stimulus level, becomes compressive in a large intermediate range of stimulus levels, and becomes again linear with a much lower gain at very high stimulus level. According to this evidence, we've used an hyperbolic tangent function which can reproduce easily this behavior, because it goes from 0 to 1 within a typical level interval. And we can set this only two free parameters. The value of this gamma A, the active damping coefficient, and this xc hat, the typical level at which of the BM displacement at which the nonlinearity becomes important. With these two parameters, we can introduce this function which describes this anti-damping term. I call it anti-damping because it's an additional force proportional to velocity. It's proportional to velocity, and the coefficient is an anti-damping coefficient for this reason. Its mathematical function has been chosen involving the square of the basilar membrane displacement xc, because it is from psychoacoustics, from Otoacoustic emission measurements, we know that the nonlinearity is a cubic nonlinearity, and so this term in a Taylor expansion is a quadratic term. And so in some amplitude interval, this behaves correctly as a cubic term. From our numerical experiments, our nonlinear active model produces this BM response. This is the BM response as a function of the position x, and I want to show you some details of this response. You see that in the peak region the response is linear at low stimulus level, again linear at high stimulus level, but it is compressive in an intermediate stimulus level. The peak moves a little towards the base at increasing stimulus levels, and the response is always linear, far from the resonance. This is these features are common with real experiments. So in this respect, the model is accurate enough to simulate the basilar membrane responses measured by laser interferometry on animals. Of course, the parameters of the model, and in particular the gamma A that I mentioned before, and the difference between gamma passive gamma, the passive damping gamma BM, and this parameter of the model gamma A, the active level of damping, is what defines the gain difference between the low level and the high level response of the system, which is shown in this picture. In this figure you see the response of the BM at the peak, in the peak region, as a function of the stimulus level as computed by the model. You see the horizontal displacement between the two asymptotic straight lines corresponds to the active gain of the system associated with the outer hair cells additional force. In this case you see that it's just 20 dB, whereas in a real cochlea it could be up to 40 dB. This would make the system more nonlinear and the solution more expensive and less stable. But this is okay. This is the output of the model, and is qualitatively similar to what one gets with BM experiments on animals. I would like to point out something that you probably already know, that this nonlinear property of the basilar membrane implies the generation of distortion products inside the cochlea, and this is very important from a musical acoustics point of view, because we can perceive these distortion products that are produced inside the cochlea. The most important ones are the cubic distortion products, intermodulation distortion products, starting from two pure tones at frequency F1 and F2 in ratios between 1 and 1.5 typically. We get very strong distortion products at these two frequencies, particularly the first one, and these tones are not present in the ear canal. They are generated inside the cochlea, and when they are generated inside the cochlea, they produce a traveling wave at this frequency of the distortion product that travels to its tontopic place and produces eventually the hearing sensation of this particular frequency that is not in the signal in the outer ear or in the environment. So when you hear music, you add some notes that are not in the have not been explicitly written by the composer, but he probably knew that you would have heard them when he wrote the music. And it's interesting to note some trivial fact that when the primary tones are in some special ratios, interval of fifth, fourth, and third, major third, you get DPs at the consonant frequencies. Of course, because the difference between 2F1 minus F2 and F1 is the same as between F1 and F2. So if F1 and F2 are in a ratio between small integer numbers, also 2F1 and minus F2 and the other one are are proportional to nearby small integer numbers. So in the first case you have 5 and 1, in the second case 4 and 1, in the second case 5 and 2, in the other 6 and 3. And so you get a very nice consonance between the notes in the present in the outer ear and those that you create inside the cochlea through nonlinearity. Up to now we've not talked about otoacoustic emissions because the cochlea is designed to carry the sound from the outer ear to the inner ear and process it there. There is no utility, no usefulness for reflecting back part of the power. But the cochlea does it anyway, so we have the opportunity to measure part of this reflected energy, which eventually gives rise to otoacoustic emissions measurable in the ear canal. The important fact is that these otoacoustic emissions are very sensitive to the level of the local basilar membrane displacement. By local I mean the place where they are generated. Usually this place is very close to the tonotopic place of that frequency. So we get with otoacoustic emissions some frequency specific information about the functional status of the cochlea, which is important for a diagnostic technique. But the generation mechanisms are quite complex, so this is just a part of the story. We have to go into more details to understand how to optimize the diagnostic effectiveness of otoacoustic emissions. To measure otoacoustic emission, we have to fit a probe in the ear canal. The probe contains miniaturized microphones and loudspeakers. The problem is that they are usually not very high quality, so we are trying to make some work to improve the quality of these detectors and microphones. Otoacoustic emissions are already used for newborn screening. You know, in hospitals they measure otoacoustic emissions typically evoked by clicks, by pulsive stimuli, and absence of otoacoustic response is considered as a negative screening test, suggesting the physicians to perform other more accurate tests. But this is not the most we can get from otoacoustic emissions. They could also be used for the early detection of mild hearing loss after we solve some problems that I'm going to talk about. The definitions: transient evoked otoacoustic emissions are evoked by transient stimuli, which can be clicks or tone bars. These techniques permit us to separate the stimulus from the response in the time domain, which is a very effective technique to get rid of the stimulus, of course. In the distortion product of acoustic emissions, we measure the lower frequency distortion products. In this case, the separation between stimulus and response is performed in the frequency domain, which is also very easy, because the difference between F1 and the distortion product is 20% or so. It's not difficult to separate them with Fourier analysis. In the case of stimulus frequency otoacoustic emissions, we evoke the response at the same frequency of the stimulus with a continuous tone. So we have a simultaneous stimulus and response at the same frequency. In this case, we can use the suppression properties of the cochlea to use differential techniques that permit us to cancel the stimulus and get only otoacoustic emissions. But we can also rely on the time frequency filtering techniques, because the stimulus frequency response has a rapidly rotating phase, whereas of course the stimulus has constant phase. So we can separate them even without suppression in the time frequency domain. And this is something I will talk to you about later. There are two main generation mechanisms for otoacoustic emission. One is the nonlinear distortion that I mentioned before, that produces a traveling wave at the dp frequency in this region. This is the longitudinal position along the cochlea. In this region you have overlap between the excitation of the cochlea at this frequency f2 and this frequency f1. In this region you have both frequencies exciting the same region. In that region, distortion produces a tone at this frequency FDP, which propagates backwards towards the ear canal, and we detect as acoustic emissions, but also goes right to its tonotopic place, where it is resonantly amplified and partly reflected back. So in this case we have two components that sum vectorially with amplitude and phase, and so what we get is a complex signal associated with distortion products generated by nonlinear distortion and by subsequent linear reflection. Linear reflection is the main mechanism for generating stimulus frequency and transient evoked emissions. In this case, nonlinear distortion is negligible, but the reflection is produced by cochlear roughness, which is random fluctuation of the basilar membrane impedance. Without roughness in a smooth cochlea, you can demonstrate that there are no reflections, no power is reflected back, there is just absorption. In rough cochlea you have reflections, and these reflections are proportional to the amplitude of the basilar membrane vibration. So it is a good diagnostic, the level of the reflected wave of the functional status of the cochlea in the resonant region. Due to the different generation mechanisms, you have different growth rates, input-output function, for otoacoustic emission produced by nonlinear distortion and by linear reflection. And also you expect different phase frequency relations. So the relation between phase and frequency is exactly flat phase as a function of frequency for nonlinear distortion generation. And this is a consequence of the scaling variance of the cochlea. The cochlea is a scaling symmetric system, which means that the physics is not dependent on the frequency scale. When you change frequency, you just move to a different part of the cochlea, but the physics is exactly the same. So the phase of the reflected wave of the nonlinear distortion waves is the same independently of frequency. This is something I should have more time to discuss, but please believe me. And so we can understand what mechanism has generated otoacoustic emissions from the slope of the phase. If it is nonlinear distortion, we expect flat phase. If it is reflection, we expect rapidly rotating phase. In the case of distortion products, this superposition of two components, one with flat phase and one with rapidly rotating phase, implies fine structure in the amplitude, because the two components are in phase and out of phase periodically along the frequency direction, and so you get a spectrum with huge oscillations that are very large when the two components have the same size, of course, as in any interference phenomenon. And this is a problem with the diagnostic power of distortion products, of course, because usually distortion products are clinically measured at a few frequencies, like audiometry. And if you by chance hit a minimum or a maximum of the fine structure, you get a 20 dB response, higher or lower than the average. and this is not good for a diagnostic of hearing based on the measure of the level, of course. And for this reason, we have implemented this chirp stimulus technique to measure high resolution spectra, to separate the two components and get almost flat amplitude spectra for the two components, getting rid of this interference. So also the ratio between the two components tells also something more about the cochlear physiology. To disentangle these contributions, we use a time frequency analysis in which it's very easy to recognize the two components. You have a strong component at zero latency or phase gradient delay, more correctly, because we measure spectrum and the gradient of the phase is this measure of characteristic time. And this large component is from directly coming back from nonlinear distortion. This higher latency component is coming from linear reflection from the FDP place. And in this case, you also understand why we are using time frequency analysis, because it is very easy to design cutoffs to filter these components in the time frequency domain, whereas the usual way to do this job was to use the inverse FT, inverse Fourier transform, and time domain filtering. But using time domain filtering of the inverse Fourier transform with a single cutoff, you do something like that or like that in the time domain plane, which is not the best choice for a signal which is naturally going along hyperbolic iso curves because of the particular scaling symmetry of the cochlea. What I mean is that in the cochlea, the right coordinates are not latency or frequency, but some quasi-hyperbolic curves describing high isophysics, a scaling invariant relation between delay and frequency, which corresponds to the particular version of the scaling symmetry, approximate scaling symmetry, that applies to that particular ear. And so by using time frequency analysis, we can even do something more elaborate, like separating these two components you see in this region and in this region of stimulus frequency emission, which are all generated by reflection, but we assume they are generated from reflections from different regions of the cochlea. The longer latency component coming from the peak region, and the shorter latency component coming from a region more closer to the base of the cochlea. If you remember that the behavior of these two regions is different in terms of nonlinearity, if you recall the simulations, this region is approximately linear at all stimulus levels, whereas the peak region is strongly compressive in the intermediate range. So we expect different growth rates for the components that we separate in this way according to their phase gradient delay. And this is what we get with the spectra, different spectra at a different stimulus level of otoacoustic emission, stimulus frequency, and transient evoked. And this is what we get in terms of their growth rates. You see the components that we assume come, the open circles come from the peak region, grow in a compressive way, whereas the components that with shorter latency that we assume reflected by more linear VM regions have a closer to linear growth rate. And even the triangles are components with double latency that we expect to be associated with double intracochlear reflection, because the base reflects back, the stapes reflect back part of the energy of the otoacoustic emissions that go back to the resonant place, are again amplified and come back again. And in this case, you get twice the compressive factor of the amplifier because they experience twice the resonant amplification in the peak region. So everything is rather coherent in this approach. So we think that this interconnection between studies of cochlear mechanics and development of otoacoustic emission data acquisition and analysis technique may allow us to improve significantly the otoacoustic emission diagnostic capability. Thank you.
Thank you. I'll ask a question first. Could you go back to your slide with the time frequency analysis? I suspect some people, myself included, are perhaps not as familiar with this kind of analysis. Yeah, this guy here. So could you just talk us through as if we don't know what time frequency analysis you're doing here, because everybody's used to spectrograms and FFTs and this kind of stuff. So how is this different from that?
Okay. Now I was in a hurry because the time was running.
Sure.
Now I feel authorized to take some time. So thank you for the question. What I mean by time frequency analysis is just a wavelet transform. I apply a wavelet transform to either this complex spectrum in the case of distortion products and stimulus frequency emissions, because in that case I have a complex spectrum as the output of my measurement, or to the time domain signal. In the case of transient evoked emission, I apply the wavelet transform to these signals. I can do it starting from the time domain, or the frequency domain is the same. And in this case, it is distortion products. What I do to get this picture is also to average the wavelet energy. These are called the wavelet components, those appearing in the wavelet transform. These are not the components, these are RMS averages on a time step which is inversely proportional to frequency, which is related to the time resolution of each wavelet component. Each wavelet component has a different time resolution, so we average the energy over a time length which is proportional to that resolution to get these nice pictures without high frequency oscillations, which are characteristic of the wavelet coefficient behavior in the time along the time direction. It's just to show the distribution of the energy in the time frequency plane. What the vertical coordinate is of course phase gradient delay in the case of distortion product. When you start from a complex spectrum, what you measure is a time which is the derivative of the phase as a function of frequency. So in the case of the complex spectrum, it's important to measure the frequency and phase, the amplitude and phase with the good frequency resolution to get unambiguously the phase behavior. Otherwise, these horizontal coordinate gives random distributions or aliasing or something worse.
And is this the kind of plot that you're able to produce clinically, kind of in real time?
Yes, I can produce it in real time because this wavelet transform is not very much time consuming, also because I perform it in the frequency domain, not as a convolution in the time domain, but as a product in the frequency domain. This implies having to do with matrices that have two frequency indexes, but you cannot, there is no ambiguity, because one is the identity of the wavelet in terms of its characteristic frequency, and the other is the continuous, ideally continuous frequency axis, which is the conjugate variable of time. So you have to perform Fourier transforms in that frequency coordinate, leaving the frequency identity as the other index of the matrix. And it's much faster to do everything in the frequency domain, of course. And we also performed some techniques to adaptively choose these cutoff curves according to the distribution of the energy in the time frequency domain, which is slightly different from each individual to the other. But all individuals have these characteristics, very similar. And so we say that the natural way to look at cochlear signals is the time frequency plane, because in this plane you can easily see this characteristic relation between these variables, time and frequency, which are related by exact inverse proportionality in any scale invariant model, and approximate inverse proportionality, some power law with a different exponent, in the approximate version of scale invariance that is characteristic of each individual ear, with very small variation. The exponent goes from 0.5 to 0.8 actually in the real cochlea. And this is related to violations of the scaling symmetry, which are related to the fact that the frequency resolution of hearing is not equal at all frequencies. It goes better, improves at higher frequencies. And this is a violation of the scaling symmetry, one of the two main violations. The other one is the fact that at low frequencies, the Greenwood map describing the relation between position and frequency is not exactly logarithmic. And this introduces another violation of this symmetry.
That's below 400 hertz or something.
Yes, but it starts to be noticeable at 1 kilohertz in this context.
Has anybody else got a question?
You mentioned the validation of your model of using
The validation?
Yes, the validation of your model using the experimental data. And you mentioned laser vibrometer, but you measured only animals.
Yes, the problem is that measurements of the basilar vibration velocity, of course, are possible only on animals or dead humans, but of course on the cadaver there is no active filtering amplification, and so they are not interesting measurements. Also slightly horrible. And, but on the other side there are very good measurements on the cadaver middle ear, because in that case the system can be studied even without is passive, without living being turned on. And you mentioned the Otoacoustic emissions provide some good test of the behavior of the model, because you can predict a lot of details of the acoustic emissions with your model, and you can measure them with sufficiently accurate acquisition and analysis systems. Because, for example, these two components of distortion products are predicted by the model to be in a particular amplitude ratio dependent on the frequency spacing between the two and the level of the two. So we have a huge parameter space to explore both in real experiments and in digital numerical experiments, and they should match if the model is correct. And of course we have to be able to separate effectively these components also at a low stimulus level where the signal to noise ratio is not very good. So there are technical problems on both sides, but this is the way we are validating the model.
This model can kind of tell what is happening.
Yes, the purpose of the model is not for playing with it, but not only for this. But it should, yes, it should help us to predict something outside the range of possible experimental tests, and this is what we build the model for. But it is a process that continues and refines itself in time. We have to do a lot also from the experimental point of view and data analysis point of view. The point that I always want to stress is that it is important in this kind of research to have everything under the control of a few people strictly interacting between each other, because very large communities cannot communicate well enough to do some coherent work on such a complex subject.